So chapter 8, hypothesis testing. Section 1 is steps in hypothesis testing with the traditional method of it. So we'll go through a few different methods for how to test a hypothesis. And I think we'll talk about the second method. Well, I'll talk about it in my lecture video for Monday, but today we'll just do the first method. So in this chapter, we're going to talk about an inferential method called a hypothesis test. And this is going to analyze evidence that your data will provide, and it's going to help you best make a decision based on the data. So you get your data, you collect it. How do you decide how to analyze it, or what decision or what conclusion to arrive at based on your data? So there's some major methods for making statistical inferences about a population. So the first one is the traditional method, which is what we're going to go into today. Basically, that's what we'll just spend all of today doing. And then the p-value method, which is going to be discussed in Monday's lecture video. And then the confidence interval method, I don't think we even actually do. I think we cut that out for the summer class. I could be wrong, but I'm pretty sure that I'm skipping that section. The main goal in many research studies is to check whether your data collected supports your statement or prediction or your hypothesis. So maybe you're doing your project on, you want to see what percentage of people, I don't know, like chocolate ice cream over vanilla. I don't know. This is a dumb question, but this is what I'm using. So let's say that's what you're doing, and you want to gather your data, but you want to make sure, or first you want to see if your data actually supports your claim or your prediction. So maybe you're predicting that 75% of people prefer that ice cream to this one, but you need to gather your data and then decide how you're going to make your conclusion, or what your decision is in terms of your hypothesis or what you thought might happen. So whether or not you realize that you all will have a research hypothesis that we will really form in part 3 of the project. So a statistical hypothesis is a conjecture about a population parameter, and this may or may not be true. So maybe I think that 75% of the population prefers chocolate ice cream to vanilla. That's just my hypothesis, but it may or may not be true. It could totally be false. So each significance test actually has 2 hypotheses. So we have the null hypothesis and then the alternative hypothesis. So 2 types, which might be kind of weird and unfamiliar that there's 2 different types, but we're going to go into each of those just a little bit. We're going to do a lot of practice with forming the null hypothesis and the alternative hypothesis. So hopefully after today, you guys should be pros at this. Okay, our first one is called the null hypothesis, and it is represented by writing an H with an O. Honestly, I really don't know. Well, I guess I don't know why it's really an H-O. Yeah, I really don't know if I could tell you why it's an H with an O or a 0, whatever. But that is what it's denoted by. So if you see H sub O, that represents the null hypothesis. And this is a statistical hypothesis that states that there is no difference between a parameter and a specific value, or that there is no difference between 2 parameters. Okay, this might make absolutely no sense right now. I promise once we do some examples, you'll see what that means. But just know that we tend to want to reject the null hypothesis. So usually we've got the null and the alternative hypothesis, and we tend to want to reject the null hypothesis. So we kind of assume that it's true, and we look for enough evidence to say that it's actually incorrect. So the alternative hypothesis is the one that you want to accept. It will make more sense when we do an example. So the alternative hypothesis is denoted as H sub 1. I've also seen it as H sub A. Rejecting the null feels good. Yeah, there's a lot of memes about rejecting the null hypothesis. Maybe I'll pull some into class on Monday or during my lecture video. So the alternative hypothesis is denoted as H sub 1 or sometimes H sub A, but our book does H sub 1. I actually used to do H sub A, but so that is how we denote the alternative one. The alternative is a statistical hypothesis that states the existence of a difference between a parameter and a specific value, or states that there is a difference between two parameters. So like this says, we want to accept the alternative hypothesis. So if the null hypothesis is rejected, then we have to accept that the alternative is true. So we'll do some examples. Here's a little note here though, before we actually do some examples writing these. So HO will always have an equal sign. And the alternative hypothesis will have a range of values that are alternatives to the one in the null. So this will make more sense in a second, but just for the sake of going over that. Okay, so let's do some examples here. Like it says, the null and the alternative hypothesis are always stated together. So you'll always see a null hypothesis and then an alternative hypothesis, or you will have to state what is what based on the scenario that you're given. So let's go ahead and write down some examples of what this looks like. We have a few different types of tests when it comes to hypothesis. So like we said, this is all on hypothesis testing. So once we form this like null and then alternative hypothesis, we have a few different like types of them. So we have what's called a two-tailed test, a right-tailed test, and then a left-tailed test. It's not super confusing. Once you see it written out, you'll see why it's called what it's called. So let's just write out some examples so you can see what this actually looks like. So for the sake of going over what we're doing today, we're going to be talking about the mean. So we're going to be thinking about the population mean, and we're going to be making claims or forming hypothesis about a mean of a population. So you'll notice that in my null and alternative, I will be using mu, and that's just because I'm going to be talking about population mean. And all of our examples today will be on population means. So this is good for any of you that are doing your projects on the means. If you're seeing if there's a difference between the mean of two groups, this is good for you. And we will touch on doing testing with proportions next week at some point. So an example to start off with is going to be a two-tailed test. So my null hypothesis, so it's going to be denoted by HO, and then you just do a colon. And like it says above, your HO or your null is always going to have an equal sign in it. So I'm going to claim that my mean, so mu, I'm going to say my null hypothesis is equal to this value k. This is just any number. So I'm just saying k for now, but in the examples below, we'll use a specific number. So then my alternative is something like maybe mu is not equal to k. You can see how you have a null and then something that's an alternative. So you have something where we say mu is equal to k. Okay, but the alternative to that, maybe it's mu is not equal to k. So the reason this is called a two-tailed test is because for mu to not be equal to k, it could fall on either side of k. It could either be less than k or it could be greater than k. So we call that a two-tailed test because there's like two sides that we're considering. So either it's on the right side of k or it's on the left side of k if it's not equal to it. Now, let's see how this is different from a right-tailed test, which only talks about one side of k. So my null hypothesis is mu is equal to k, and maybe I'm doing a right-tailed test. So I want to see, or I want to have my alternative hypothesis be that mu falls on the right side of k. So mu is greater than k. So my alternative can be that mu is greater than k. And that's called a right-tailed test because that means that it would fall on the right side of k. And k is just some number, like I said. When we do an example, we'll have an actual numeric value. So you can probably predict when we have a left-tailed test, the null is going to be, again, mu equals k, and then your alternative will be that mu is less than k, because we're doing a left-tailed test, so it'll be on the left side. So two-tailed test, mu can be on either side. Right-tailed, it can be on the right side. Left-tailed, it can be on the left side. Like we said above, usually we want to reject the null hypothesis. So whatever we think or whatever we are going for in our test to be true is going to be our alternative. So we're trying to gather enough information to reject the null. So let's do some actual examples so you can see how this would play out. So we have 3 examples here. Oh, let me plug in my, hold on. All right, we're good. So I have 3 examples here. One will be a two-tailed, one will be right-tailed, and one will be left-tailed. So my first one says, a researcher thinks that if expectant mothers use vitamins, the birth weight of the babies will increase. The average birth weight of the population is 8.6 pounds. Okay, so let's think about what this is telling us. Our researcher thinks that if the moms use vitamins, the birth weight will increase. So they think that the birth weight will be greater than 8.6 because 8.6 is the average birth weight of the population. And our researcher says, okay, maybe if we try giving the moms vitamins, the birth weight will increase. So the null hypothesis is always the one that we want to reject. And the alternative is what we hope to accept through rejecting the null hypothesis. So if my researcher thinks that the birth weight will be greater than 8.6, that's what I would like to accept as being true. You don't go into an experiment with a hypothesis, and I mean, at least I don't think usually you go in wanting to reject what you think is true. You want to gather enough evidence to conclude that what you thought was correct. So if the researcher wants to or thinks that the birth weight is going to increase, that's going to be our alternative hypothesis because that's what we want to accept. So our alternative is going to look like mu is greater than 8.6 because our researcher thinks that if we use vitamins, the birth weight of the babies is going to increase, which means it will be greater than the mean of 8.6. Okay, the null hypothesis is always just mu equals something. So if you're dealing with means, it's always just an equal sign and it is the same number as the alternative. So it's literally just mu equals 8.6. So it is just equals to, it's not less than or equals to. Intuitively, that might not make a lot of sense. And you might want to say, well, why wouldn't the null be like mu is less than or equal to 8.6? Honestly, in reading through the textbook, I could really just gather that that's basically common practice. So I don't have a great explanation for why that's the case. Maybe I can try and find one. So the null is always mu equals whatever that thing is that's also in your hypothesis test. So we want to gather enough information to reject the fact that mu equals 8.6 and then accept the fact that mu is greater than 8.6. That's our goal. Doesn't always happen, but that's our goal. All right, B, a contractor wishes to lower heating bills by using a special type of insulation in houses. The average of the monthly heating bills is $78. Okay, so our contractor wishes to lower these heating bills. So we want to lower them. So we want to make the alternative hypothesis what we want to happen. So the alternative is going to be that mu is less than $78 because we want to lower them. Okay, well, that means that our null hypothesis is just going to be mu is equal to $78. All right, let's try C. So a psychologist feels that playing soft music during a test will change the results of the test. The psychologist is not sure whether the grades are going to be higher or lower. In the past, the mean of the scores was 73. Okay, you can see the difference here that in the past two, we had a goal. So the researcher thought that the weight would increase. The contractor wants the heating bills to decrease. In part C, we're going to try something. So we're going to try playing music to see the effect, but we don't really know if it's going to be better or worse. But we think it's going to have some form of an effect. I don't know, maybe the music's distracting and people actually perform worse, or maybe it's calming for some people and they perform better, but we don't know. So we're unsure. So we can't say that the mean is going to be higher or lower than 73. So our alternative is just going to be that mu is not equal to 73. And this is what's called that two-tailed test, where you don't have an idea if it's going to be higher or lower than the mean, but you just think it's going to be different. So it could end up on either side of the mean, and that's your alternative. So that means our null hypothesis is just going to be 70, mu is equal to 73. Okay, this is the first step whenever you're doing some form of study, is you're going to come up with some null or alternative hypothesis. So once you come up with this, then you'll select the right statistical test, and then you'll choose your level of significance, and then you're going to form a plan for conducting this study. But your first step is to come up with your null and alternative hypothesis, which is what we just did for these three scenarios. So are there any questions on the answers that I wrote down or how I got them? Okay, cool. Let's keep going. So like I said, after stating this, this is definitely not in my notes. I don't even know. So I have two versions of these lecture notes, and I don't know if this is supposed to be in here. Hold on. I think these were like notes for whoever was lecturing, because I definitely don't have these in the version that I posted on Canvas. Okay, we're just gonna skip this because this is the first time I'm seeing this thing. Okay, move on to our next definition. So now we're going to define what is called a statistical test. So like we said, after stating your hypothesis, you're going to select your correct statistical test. We're going to get into these after we go through section 8.1. So we're going to go through two different types of statistical tests after that, but just know for now that this uses the data obtained from your sample to make a decision about whether the null hypothesis should be rejected. So this literally is just a type of test that takes your data and helps you make a decision on whether you want to reject it or not. And we'll get into some examples of that. A test value is a numerical value obtained from your statistical test. Like I said, this might not make a lot of sense until we actually use a type of statistical test. So you'll see what this looks like once I do an example. Okay, but before we get into a specific type of test, let's discuss some errors that could happen with doing hypothesis testing. So we have two types of errors here. We have what's called a type 1 error and then a type 2 error. So when the null hypothesis is true, a type 1 error occurs when you actually reject the null hypothesis. So let me write that down. When we reject. Okay, so this happens when the null is actually true, but we reject it. So that's an error because the null was actually true, but we said we gathered enough evidence to reject it. So that's definitely a problem. That's an error. But we could also have another type of error where the null hypothesis is false and we don't reject it. So a type 2 error is going to occur when the null is false and when we don't reject the null. Oh, okay, so those are our two types of errors here. You can see why both of those are problems because one thing was true and we said we gathered enough evidence to do the opposite of what was true. So that's definitely a problem. So we've got a little bit of like a chart here that might help you understand where the errors come from. So there should be, oh no, there. So we have right here that when we reject the null hypothesis, but the null was actually true, that's what's called a type 1 error. And then here we reject the null hypothesis and the null was false. So that would be the correct decision because the null was false and we rejected it. Then below we have where the null was true and we didn't reject it. So that's great. That's the correct decision. But then we have where we didn't reject it and it was false. And that would be a type 2 error. So you can see there's two options here where we made the correct decision and two options where we make the wrong decision. But with that being said, in some cases, a type 1 error or a type 2 error is like worse than the other one. We'll see what that really means, but sometimes the type of error is definitely worse than the other possible error. So let's show an example of why that's true. Okay, so here is a little chart here that's, oh my gosh, there's so many notes in here that I did not put in here. Okay. All right, just ignore these. I think someone put in lecture like notes for themselves in white, and when I converted the background to black, they all came through. But whatever. Okay, so here we have a little chart here that's on decision errors in like a legal trial. So this is interesting because it shows you like what a type 1 error would look like versus what a type 2 error would look like. So we have some things over here. So we've got the defendant. So if the defendant is innocent, that's going to be referred to as our null hypothesis. And if the defendant is guilty, that's going to be our alternative hypothesis. So if the defendant's innocent and then you acquit them, that means that that was the correct decision. So they were innocent and you did not convict them, so we're good. But let's say they're innocent and you did convict them. That's a type 1 error. So that's a problem. Because that is clearly not the correct decision. But what are our other options here? So they could be guilty and we could not convict them. Okay, not great. Or they could be guilty and we could convict them, and that's the correct decision. So which one is the worst error if you're the defendant? So if you're the defendant and you're innocent, but you actually get convicted, or if you're guilty and you don't get convicted. So which one's worse, type 1 or type 2 here? You can throw your answers in the chat or you can say them out loud. Yeah, good. So the innocent and convicted is probably the worst one for you. Not that it's great to be guilty and actually, not be convicted, but as the defendant, you probably wouldn't be that mad about that. So keep that in mind that sometimes, depending on what type of error it is, it's a bigger mistake than maybe the other type. Okay, that's just like kind of a fun example that just like emphasizes the different type of errors. So. Okay, so now that we've talked about our two types of hypothesis and then our options for rejecting or accepting the null and whatnot, we're going to get into what's called the level of significance. So once you think about your null and alternative hypothesis, and then you go through thinking about what study and what you're going to do, you want to decide on a level of significance. So the level of significance is the maximum probability of committing a type 1 error. This probability is going to be symbolized by alpha. So remember, the type 1 error is, here, let me just scroll up so you can see it. The type 1 error is where the null was true, but we actually rejected it. So that's not something that we want. We don't want to accidentally reject it. So when we think about doing our test, we want to pick a level of significance where the level is the maximum probability of committing a type 1 error, where the null was true, but you actually rejected it. And this is just going to be symbolized by alpha. This is just going to be important when it comes down to actually like doing the test and deciding if we want to reject the null or not. So this will be used in some of our examples. There are like 3 commonly used types of significance or level of significance. I don't think they're stated in the notes, so I'm just going to write them down. So some common, oh, that is not how you spell common. So some common ones are 0.10, 0.5, 0.1. So that makes sense because the level of significance is the probabilities that we commit an error. And you obviously don't want to commit an error. So it makes sense that you would want to choose probabilities or levels of significance that are lower. So you'd like to say, oh, maybe I did this with a 5% chance that I rejected the null, but it was actually true. So it makes sense that these are lower numbers because they're probabilities that you've committed an error. Okay, next let's talk about, I think we have like 3 more definitions and then we'll do some examples here. Yeah, 3 more. Okay, so the first thing we're going to define is a critical or rejection region. So this is a range of values of your test value that indicates if there is a significant difference and that your null hypothesis can be rejected. So when we do an example, we're going to end up finding some range or some region of values that if our test value like falls within that, then we can reject the null hypothesis. So that's what's called a critical or rejection region. And based on our test, we're going to be able to find what that region is. And then we're going to be able to place our test value wherever it falls and see if we should reject the null hypothesis or not. Next, we have the non-critical or non-rejection region, which is pretty much what it sounds like. So it's a range of values that if your test value falls within that region, it was probably due to chance and you should not reject the null hypothesis. So this is going to be the region that if it falls into that, we really can't conclude that we can reject the null because there's not enough evidence to do that. And then we have what's called the critical value, and this just separates the critical region from the non-critical region. So we'll be finding that critical value, and then very similarly to how I was graphing a normal distribution and shading in areas on there, that's basically what we're going to be doing. So you'll find an area that is a critical region where if it falls in there, you reject the null. And then your other area is going to be non-critical. So if it falls in there, we can't reject the null hypothesis. And then we have what's called a critical value, which is just what separates the critical region from the non-critical region. Okay, so we have some examples here. These aren't, man, there's more lecture notes in here. I just want to know who put these in here. Okay, we have some examples here that I'm going to draw graphs for. Unfortunately, this is like right in my way where I was going to draw these graphs at. Okay. So I'm going to come up with 3 examples here. So I'm going to do a right-tailed test, a left-tailed test, and a two-tailed test, since those are our 3 types. And I'm just going to pick a significance level. So like I said, there's a few types. So I think I wrote down like 0.10, 0.5, and then 0.1. So I'm going to pick a significance level of 0.1. That just means at this level, there's a 1% chance that I made a type 1 error. And whatever significance level you pick is going to change what your critical region is. So, if you want less of a probability that you make a type 1 error, that's going to change what your critical region versus non-critical region looks like. All right, so my first example, all of these I'm going to make alpha 0.01. Okay, so let's do the right-tailed one first. So surprise, surprise, I'm drawing a normal distribution. I think I've gotten better at these though since I started teaching this class. Okay, so my critical region is going to have an area of 0.01. And that's because I chose a significance level of 0.01. This is going to seem very, very similar to what we've done in the past. The same way that we would say, oh, we want this area to be this much or this probability to be this much. So we use our chart and we find the z value or the z-score that's associated with that area. Same exact thing. So that's exactly what we're doing here. Now we're just using this concept to do hypothesis testing. And we'll use it for some actual examples, but for now, I'm just going to draw some graphs so that you can have an idea of what this looks like. But you'll always be given a context or a scenario that you'll be able to use for this. So my right-tailed one means that I want doing a right-tailed one, so it's on the right side. And my significance level is 0.01. So I want to find the value here that makes this area 0.01. This is going to be known as my critical region. And if my test value falls within there, that means that I have enough evidence to reject the null hypothesis. This is going to be known as my non-critical region. And we know that this area is going to be 0.9, sorry. Okay, so all that means is that it's a right tail test with significance level of 0.01, which means in that right tail, in my critical region, I want to have an area of 0.01. So all you have to do is go to your chart and find the value associated with 0.01, with this area being 0.01. So I'm not going to go through doing that because I've done that, I feel like, so many times. So if you want that area to be 0.01, it means that the area to the left of this value should be 0.99, and you can use your chart to find what that number is where that's true. I'll just tell you for the sake of it that it is 2.33. Also, these are all in the book because these are really common, the significance level being 0.01. These are all listed in the textbook. So I actually have like a little image of a chart that shows you for the 3 most popular significance levels for the left-tailed, right-tailed, and two-tailed tests, what these values are. So you don't need to go through the process of like looking them up every time because there's like a little cheat sheet or like chart type thing that you can look at. But for the point of like introducing it, I'm just showing you how they got these values. So yeah, but not like every time you do this, you have to go through this like whole long process. But for the sake of introducing the topic, we're going to go through the long process. Okay, so let's now do the left-tailed test, which is very similar. So I'm going to draw same thing. And I want what is in the left tail to be 0.01. And this is the critical region. It's almost the same as the last example. It's just now in the left tail. So this over here is my non-critical region. But if you remember anything about the normal distribution, they are symmetric. So just because I now moved, like I wanted my right tail at first to be 0.01, well now I want my left tail to be 0.01. This is going to be the same value. It's just going to be negative. So it's negative 2.33. That like am I literally forgetting the name of it? The critical value. There we go. So these ones are not too bad, but the two-tailed one is slightly different and it has like an extra step, but you'll see why. So the two-tailed one is different because now we have area that we want in both tails. So remember how when we introduced it, I said, oh, if you're doing the two-tailed test, it's because you're not saying that this value is going to be greater than something or less than something. You're just saying it won't be equal to it. So it can fall on either side. So now we have to do a two-tailed one where we're not just concerned about an area on the right side or the left side. So if we're doing a significance level of 0.01, that means that the combination of the area in these two tails should be 0.01. So each one of them, so 0.01 divided by 2 is equal to 0.005. So each one of my tails should have an area of 0.005, because if I add these together, then I get a total area of 0.01. So the only difference between the one-tailed or the left-right-tailed versus the two-tailed is that that significance level, or the alpha, has to be divided amongst the two tails evenly. And those ends there, so the ends are your critical region, and then the middle becomes your non-critical region. And by using the chart, you see that this is negative 2.58, and this is 2.58. And like I said, these values are very standard, and there's like a little guide to what's what. I meant to put it in the lecture notes, and I totally forgot to. But I have a screenshot of it, so I'll include it on Canvas or something, or it's in the textbook too. This is just like a visual of what you would do if you were performing a hypothesis test and you had an alpha of 0.01 and you were doing a right-tailed or a left-tailed or a two-tailed. So I know that it's a little weird and confusing because we don't have like any example that we're doing this for. But as soon as we get into the next section, we're just going to do an example, and I think it'll be better. Okay, so at the bottom here, it just gives you some steps for finding the critical values for a specific alpha. So this is what we just did essentially, but let's just read through them. So if you ever need to look back on how to do this, you can. So first you draw your figure and indicate the appropriate area. So up above, when I had my significance level of 0.01, I drew my little normal distribution and it was right-tailed. So I shaded in on the right side my critical region, which I want to be an area of 0.01. So first step, draw that and indicate the critical region and what you want. So like it says, if the test is left-tailed, the critical region with area equal to alpha will be on the left side. The test is right-tailed, the critical region with area equal to alpha will be on the right side. And then if the test is two-tailed, alpha must be divided by 2, half the area on the right and half the area on the left. And then step 2, it just says for a left-tailed test, use the left-tailed test, use the z-value that corresponds to the area equivalent to alpha. If it's a right-tailed test, you have to do that trick that we learned where you do 1 minus alpha. And then for a two-tailed test, use the z-value that corresponds to alpha over 2. And then for the left one, it'll be negative, and then change the sign so the right one is positive. These are just some steps in case you forget how we've done this in the past or need like a refresher. But like I said, you probably won't have to go through finding like these values. Okay. So let's come down here. First, we're going to do 3 more examples of what I just did. So we're going to do the same thing all over again, just with some different numbers. And I'm now realizing I forgot to change the numbers because I wanted to do different ones than what I did. So if you have your lecture notes out, just do me a favor and change these really quick. So this one I'm doing is this. I just didn't want to do ones that I'd already done before. Oh, and I think I left the last one. Yeah, I did. Okay, so we're gonna do the same thing that I just did above, just for some different significance values, just to get some more practice doing it. So let me get some water and then we'll do this. Okay. So it wants us to find the critical values, draw the figure, and then show what the critical region is. So first step, I'm just gonna draw my little chart, my little normal distribution. I'm doing a left-tailed test with a significance value of 0.10. So I know that on the left side, I want this area to be 0.10. And that is my critical region right there. I'm just gonna start abbreviating this. So that means that the rest of this is my non-critical region. Okay, well, if I went to my table and looked up what this value would be for an area of 0.10, I would get negative 1.28. All right, let's try the next one, which we're doing a right tail test with alpha equal to 0.005. So if I just draw my distribution, I know that in this right tail, I want a critical region with an area of 0.005. Okay, well, if I want to find the z value associated with an area to the right of 0.005, I need to look up on my chart 1 minus 0.005. And this will just give you a value of 2.58. Let's do the last one, which is a two-tailed test with alpha equal to 0.1. All right, well, that means that in each tail, I need half of this. So 0.1 divided by 2 is going to be 0.05. So that means in these two tails, each I need an area of 0.05. And this is a critical region, and this is a critical region. This has an area of 0.05, and this one has an area of 0.05 as well. So if I go to my little z-score table and look up these areas, you should get negative 1.65 and then 1.65. Okay, so let's just look at this little procedure here for actually doing your hypothesis test with the traditional method, which is what we're going to do actual examples for now. So step one is to state your hypotheses and identify your claim. So you're going to state your null and alternative and identify which one is what you're claiming. So remember, your alternative hypothesis is always what your claim is. Then you're going to find your critical values from your appropriate table. So we use the z-score table, but you'll see that we can also do this with the t-test, not just the z table. So if you remember last chapters, we talked about the z distribution and the t distribution. We'll see in a later section that we can also do this with that t distribution table, not just the z distribution one. Then we're going to use whatever test we're doing to compute the test value, which we will do that in the next section in just a few minutes. Then we're going to make a decision on whether we reject or not to reject the null hypothesis, and then you summarize the results. I know it sounds like a lot, but believe it or not, it's a lot of stuff that we've done before. Okay, so I do want to do some actual examples with this stuff. Are there any questions before I move on to actually doing an example? All right, I'm going to open the 8.2 notes then, and then we're going to try this out. We're not doing all of section 8.2 today because section 8.2 talks about two different, I don't know if I want to call them tests, I guess. So it talks about two different types of tests using this stuff. And I thought, let's just stick with one for today, because honestly, trying to do another type just seems like an overload on information. So we're just going to do 2 pages of lecture notes in here, and then I will do the next type of test in my lecture video for Monday. It seemed like way too much to try and do all of that. Okay, section 8.2, z-test for a mean. Okay, so now we're going to use everything that we just talked about in the last section, and we're going to talk about what a z-test is and how to use everything we just learned in order to use a z-test and decide if we're going to reject the null hypothesis or not. Okay, so 8.2 z-test, and there's another type of test in here, but we'll get into that later. So recall that a statistical test uses your data obtained from a sample to make a decision about whether the null hypothesis should be rejected. Yep, we just talked about that. Further, the numerical value obtained from a statistical test is called the test value. So now we're actually going to get into the test value. So I know we defined it a little bit ago, but we didn't really do any examples with how to find a test value or what statistical test we're using. Now we're actually going to do an example of using what's called a z-test, and you'll see how this all works together. So you'll notice that our statistical test will resemble the general formula for a z-score. So if you remember before when we were taking information and computing a z-score and then going to our table and finding the value associated with it, it looked a lot like doing the same thing that we're going to do here. So for our z-test, or just in general for the test value, it looks like an observed value minus what you expected it to be over what's called the standard error. So in general, that's what the test value looks like, but we're going to get into a specific form of that with doing the z-test. So there's different types of tests, and these are different ways to compute a test value and how to decide, to reject the null or not. We use the z-test when we know the population standard deviation. So this might sound familiar because when we were doing confidence intervals, we would use the z-distribution if we knew the population standard deviation. And if not, we would use the t-distribution. Similar concept here on why we're using the z-test. So the z-test for means, it's a statistical test for the mean of a population. It can be used when n is greater than or equal to 30. So when your sample size is greater than or equal to 30, or when the population is normally distributed. And your population standard deviation is known. So this test is, like it says, more theoretical in nature because if you think about it, it's not very often that you would know the population standard deviation. It's like if you guys think about your projects that you're doing, whatever your research question is, maybe your population is just like college students. I don't know, maybe you're going for like GPA of college students. There is no way that you would know the standard deviation of the GPA of all college students. Like there's just no way. So like, that's why it says this is pretty theoretical because it's not very often that you actually know the standard deviation of your population. It actually kind of sounds ridiculous that you would know the population standard deviation. So it's more theoretical. We're still going to discuss it, but it will be a brief discussion since it is not the most applicable test in the world. It's a good one to get started on. So let's actually write down the formula. So the formula for the z-test is z is equal to, and this is going to look really familiar. So x bar minus mu over sigma over the square root of n, where x bar is the sample mean. Mu is your hypothesized population mean. And then sigma is your population standard deviation. And then n is your sample size. So hopefully these words should all be familiar, which should help. The only one that might be different is the hypothesized population mean. So if you remember when I was giving some scenarios in the last section, let's see, we talked about like the weight of newborns or whatever. So when that researcher said that she thought the weight would be over 8.6, if the moms took vitamins instead, that hypothesized population mean would be 8.6, because that's what she hypothesized. It would be bigger than that. Down here, there's just a note that says if your sample size is greater than or equal to 30, the central limit theorem allows us to use the standard normal distribution to approximate the distribution of the sample means. So this explains why when we were doing all those images, we were using the normal distribution. That's thanks to the central limit theorem that says that we can use the standard normal distribution to approximate the distribution of our means. Okay, let's talk about our steps here. So, state your hypotheses, identify the claim, find the critical values from the table, compute your test value, make your decision, and summarize. Now we're actually going to do an example of doing all of these things. All right, here we go. But we took like an hour of lecture to get to this point. So, example. A researcher reports that the average salary of assistant professors is more than $43,000. Okay, so you have a researcher, they report that the average salary is more than $43,000. Right there, you see that we've got their prediction, or like they think that it's more than that. We have a sample of 30 assistant professors, has a mean salary of $44,370. Cool. So we have a random sample of 30 assistant professors, and their mean salary is 44,370. Okay, at a significance level of 0.05, test the claim that assistant professors earn more than $43,000 a year. And then we're given the standard deviation of our population. Great. Let's go through our steps here. So first, we're going to state your hypotheses and identify which one your claim is. So remember, we have to do a null and an alternative hypothesis. So our first one is going to be, or I'll just write both of them actually. So null, and then over here, we'll do the alternative. All right, so let's read the question again and see what like our researcher is claiming. So our researcher is claiming that assistant professors earn more than $43,000 a year. Okay, so they think that it will be greater than 43,000, which means that our alternative is going to be mu is greater than 43,000. Because remember, we want to be able to reject the null hypothesis so that we can accept this alternative and say, hey, the mean salary is greater than 43,000 a year. That's what we want. I know it sounds kind of weird because like saying the word alternative almost makes it seem like you don't want to accept that. But in this case, we always want to accept the alternative. Okay, anyone have an idea what my null hypothesis would be? You can send it in the chat if you want. You can private chat it too, I don't care. All right, I will give you a hint. Very close, not less than, but super close. The null hypothesis is always just mu is equal to 43,000. Yeah, good. Super close. Yes, the null is always mu is equal to whatever that number is. So once you got the alternative, you can do the null hypothesis, because the null is pretty standard. Okay, cool. So now we've got these two hypotheses down, and then we want to identify which one our claim is. So our researcher is claiming that assistant professors earn more than 43,000. So this one right here is going to be our claim. Okay, before I go on to step 2, any questions on step 1? I don't want anyone to get left behind here. All right. Step 2 is to find the critical values from the appropriate table. So in order to do this, we need to just acknowledge what level of significance we're using for our test, and figure out if it's a right-tailed, left-tailed, two-tailed, whatnot. So let's just write these things down. We're given the level of significance. So we were told alpha is 0.05. Okay, we were also given our alternative hypothesis of mu being greater than $43,000. So does anyone want to take a shot at if this is right-tailed, left-tailed, or two-tailed? You can private chat me if you want. Awesome, right-tailed. Thank you, Michael. So this is a right-tailed test. Okay, so using that, let's go ahead and draw our little normal distribution. So I'm going to draw this out. Okay, so we have a right-tailed test, so we know that we want this area here. This is our critical region, so we want this to have an area of 0.05. And then this is our non-critical region. All right, well, for the sake of going through it, why don't I go to the table here? So let me open up the table. Okay, cool. So we'll actually go through the table for this process, just for the sake of doing it. But like I said, there's a little thing in the textbook that tells you what the values are for all of these different significant levels. So we want this area right here to be 0.05. So what we want to look for on the chart is we want to see what value is associated with having an area of 1 minus 0.05. And remember, that's because our chart will give us the area to the left of a value. So because we have an area to the right of a value, we have to do that thing where we subtract it from 1. So let's put our chart. So, all right, so we want 0.95. So, okay, it looks like it's going to be somewhere around here because right here I've got 0.9505 and 0.9495. Well, unfortunately, our area of 0.95 is right smack in the middle of these two, but we pick the bigger option. So our two options are 1.64 or 1.65 because what we want lies smack in the middle of these two areas. But we're going to choose the bigger one, which is 1.65. So come back here. So we know this value here is 1.65. Okay, and that's our critical value. That value marks the separation between your critical region and your non-critical region. That's super important because the critical region tells you where you can reject the null hypothesis and where you can't. Okay, any questions on this before I continue? Okay, the next step is to compute the test value. Okay, well, we're doing what's called a z-test, and we were given the little formula for that. So our test value is found by doing z equals x bar minus mu over sigma over the square root of n. And yes, this looks very similar to computing a z-score. So let's just plug in the things that we were given. So I'm going to write down what they are. So our x bar is going to be, let's see. So We were told that there is a random sample of 30 assistant professors and their mean salary was 44,370. Okay, so that means our sample mean is 44,370. Mu is going to be what you have predicted to be the mean. So above, we have said that we think that mu should be greater than 43,000. So that means that our mu is going to be 43,000. Sigma is the standard deviation of the population, which we were told is 5,230. And then N is going to be 30, because our random sample has a size of 30. All right, let's plug this all in. So this is equal to 44,370 minus 43,000 over 5,230 divided by the square root of 30. I'm going to grab my calculator and we're going to figure out what this number is. All right, so I got 1.43. This is what's called our test value. So we were doing a z-test, which the z-test tells you this is how you compute the test value. So we computed it, and now we're going to use the test value in order to make a decision if we want to reject or not reject the null hypothesis. Okay, so let's talk about when we can and when we can't reject the null hypothesis. So if this test value falls within our critical region, which we shaded up here on the graph. So remember, we found where this critical region is at. If the test value happens to fall in that region, that means we can reject the null hypothesis. If the test value does not fall within that region, we are not allowed to reject the null hypothesis. So given our region and given our test value, what do you guys think? Are we going to reject it or not reject it? You want to reject it. I feel that. I think everyone always wants to reject the null hypothesis. But the question is, can you reject it? No, good. Sadly, we cannot. We can't reject it because our test value was 1.43 and our critical region was anything greater than 1.65. 1.43 is less than 1.65. So that means our critical or our test value falls in the non-critical region, probably around there. So that does not work for us, sadly. So because 1.43 is less than 1.65 in our case, we cannot reject. Oh, it's terrible. The null. Okay, but what does this really mean? Like, okay, that's great and all to say we can't reject the null hypothesis, but let's think about what that means in terms of like summarizing your results. So it just means that there's not enough evidence to support the claim that we wanted to. So we wanted to be able to, I'm going to scroll up really quick. We wanted to be able to reject the fact that the mean of these assistant professors was $43,000 so that we could accept the fact that their mean salary was greater than that. Our researcher wanted to accept that the mean salary was greater than that, but we were not able to. So what that means is that we just don't have enough evidence to say that their salaries are more than 43,000 a year. So to summarize this, I'm just going to say there is not enough evidence to support the claim that assistant professors make more than 43,000 a year. That's all that means. If we were able to reject the null hypothesis, it would just be there was enough evidence to support the claim that assistant professors make more than 43,000. But let's talk about a little note here. So when the null hypothesis is not rejected, it can't be accepted as true. So just because you didn't reject it doesn't mean that all of a sudden that's the case. So just because we said, oh, we can't reject that the mean is 43,000, it doesn't mean that suddenly we say the mean is 43,000. This is like, there's not enough evidence to say that it's false. So I like this analogy here about the jury trial. So you just say someone's guilty or not guilty, because if someone's found not guilty, it doesn't mean that they were proved innocent. It just means there's not enough evidence to reach a guilty verdict. So kind of in the same way here, it's not like we say just because something was not rejected, it's true. We just say there wasn't enough evidence to reject it. So just keep that in mind whenever you're like summarizing the results. So just because something is not true, like, or we didn't reject it, doesn't mean that it suddenly we can accept it. Okay, that is all that I wanted to do today in terms of hypothesis testing, because I think it's a lot to take in, especially if this is the first time you're learning it. So I don't want to keep going. So I'm going to stop my recording.